Let's talk about symmetric polynomials. In this lecture, we'll give the definition and look at some examples. So firstly, these are polynomials in n variables. So let us think of n as some fixed natural number. And let's look at variables x1, so n is at least 1. And we look at variables x1, x2, x3 till xn. And we consider all polynomials with integer coefficients in the variables x1, x2, xn. So recall, this is the notation. Z of x1, x2, xn just denotes the set of all polynomials with integer coefficients. So let me say Z coefficients in the variables x1, x2, xn. Okay, so that's the space we're looking at, multivariable polynomials. And of course, in place of Z, we can also look at other rings or fields. For example, you can look at rational coefficients or complex coefficients and so on. For now, we'll just look at the integers. Okay, now what is a sort of the simplest example of a multivariable polynomial? It's what we would call a monomial. Okay, what is a monomial? It is just a single term of the following form: x1 raised to some power, x2 raised to some power, and so on, xn raised to some power. Okay, and a monomial is therefore determined by the sequence of powers on top. So what are the alpha i's here? The powers, they are non-negative integers. So we use z plus to denote the set of all non-negative integers. These are all integers k such that k is greater than or equal to 0. Okay, so the alpha i's, these exponents, belong to z plus for all i's. Okay, so I should say for all I equals 1, 2, 3 till n. Okay, now what we'll do is we'll encode this information as follows. So there it is, alpha 1, alpha 2, alpha n. It's actually a tuple. Okay, we should think of it as an ordered n tuple, alpha 1, alpha 2, alpha n. This is an element of z plus power n, the Cartesian product of z plus with itself n times. And this is sometimes called a multi-index. Okay, so we usually call this a multi-index. Okay, and here's some nice shorthand notation, which is very, very convenient. We write x to the alpha for this monomial. So this is just notation, if you wish. Definition: x to the alpha just denotes the monomial x1 to the alpha 1, x2 to the alpha 2, xn to the alpha. Okay, now observe that monomials are special for the following reason: that any polynomial is, well, nothing but a sum of monomials. Okay, so observe the following simple fact. So fact, if you wish, if f is a polynomial, so f of x1, x2, xn, let this be a polynomial in the n variables x1, x2, xn, then f can be uniquely written as a linear combination of monomials. Then f of x1, x2, xn can, more or less by definition, that's what a polynomial is, can be written as follows. It's a linear combination c alpha x to the alpha, where alpha runs over the possible multi-indices z plus power n, and where c alphas are all integers and only finitely of them are not 0, and c alpha is 0 except for finitely many multi-indices alpha, except for finitely many Okay, and further this expression is unique. That's the other more or less obvious fact. Okay, so this is why monomials are important. They are the most natural basis, if you wish, in terms of which a polynomial can be expanded. Here's a simple example. So we could take the polynomial f of x to be x1 cubed, x2 square, x3 power 1 plus x1 power 1, x3 squared. Now notice I use just the variable letter x here. So x here already is a shorthand for the tuple x1, x2, x3. Okay. Now, so here is a polynomial which is the sum of two monomials, and what are the multi-indices here corresponding to the first term, for example, is, so if you look at the powers which appear, so I've got the powers 3, 2 and 1, right? So they form the multi-index 3, 2, 1, and for the second term, the powers are 1, 1 and 2, and so the multi-index corresponding to that term is 1, 1, 2. So in other words, if you call this as alpha and this as beta, then the given polynomial is nothing but the sum of the monomials in our notation x to the alpha plus x to the beta. Okay, so this is sort of useful shorthand because when we start talking about symmetric polynomials, we will need to we'll be dealing with many terms, and the indices are somehow the exponents, the multi-indices will be the easiest way of describing various properties. Okay, so now to the main agenda of this lecture, which is to talk about what symmetric polynomials are. So what do you mean by a symmetric polynomial in n variables? So polynomial f is said to be symmetric. So there's a polynomial in the variables, let's say, so this is in x1, x2, xn. Symmetric if the following holds: f of x1, x2, xn polynomial is the same as f of any permutation of the variables. Okay, so if I change the order of the variables in any way I want, so let's describe it as follows. I permute, so I look at, instead of x1, x2, xn, I look at x sigma 1, x sigma 2, x sigma n for all permutations sigma. So this should be true for all permutations sigma of the numbers 1 to n. Okay, so recall the usual terminology here. The group, the permutation group Sn is nothing but the set of all permutations of n distinct symbols. So here I'm going to think of Sn as being the set of permutations of the numbers 1, 2, 3 till n. Okay, so this Sn is exactly the set of permutations of the numbers 1 to n. Okay, so any which way you permute the variables, the polynomial f remains the same. Okay, so that's the definition of a symmetric polynomial. So what are examples? So let's look at simple ways in which one can construct symmetric polynomials. So let's start with n equals 2. So two variables. So what's the property here? So I have two variables x1 and x2, and the property that I need to satisfy really is only this, that if I permute the variables like this, look at x2, x1, then the value of f is the same. Okay, so this is what a symmetric polynomial is. So this is symmetric polynomial. So let's write an example. Let's write a few different examples. So I could take, for example, f of x1 comma x2 to be, for example, just the sum x1 plus x2. Okay, here's an example of a symmetric polynomial. Okay, if I interchange the variables x2, x1, I just get x2 plus x1, which is the same thing. So this is one example. Example 2, I could look at the polynomial f of x1, x2 equals, so this is polynomial 1. Here's a second, f of x1, x2 equals, for example, let's say I want the monomial x1 square, x2 to be part of my polynomial. Okay. Now, the only way this resulting polynomial can be symmetric is if I also add in the sort of symmetrization of this, meaning I change x1 to x2 and x2 to x1. So that will become x1, x2 square. Okay, so observe now I have done the least possible to make it symmetric. This is an example of a symmetric polynomial in two variables. Let's take another one. So just like the very first one, or maybe let's take something slightly more complicated. So for example, I can take x1 square plus x2 square, which is like the first example, except I've now squared both variables. But let me now also do the following. So observe, this is by itself already symmetric, but I could also add something further to it. So let me do the following. I say this minus 3x1 x2. Okay, so observe that this resulting thing is symmetric also. Okay, why? Because the first term x1 square plus x2 square is symmetric under interchange of variables, and so is the second term. So here are some examples of symmetric polynomials. Okay, now of course you can imagine that as the number of variables increases, you can sort of construct far more complicated examples. So let me just do one for n equals 3. If I take the polynomial f of x1, x2, x3, say I want the following. I want x1 cubed, x2 square, x3 power 1. Okay, I want this monomial to be part of my polynomial f, but I also want it to be symmetric. Okay, so what's the least I should do? I need to add in some extra terms which are obtained by sort of symmetrizing, permuting the variable. So as it stands, this is not symmetric, but let me make it symmetric. Well, what will I do? I will, for example, look at permutation. So let me first interchange x1 and x2. Okay, so I will get, instead of x1 cube x2 square, I have x2 cube x1 square x3. Okay, you can of course rewrite it as x1 square x2 cubed x3. Okay, and plus what else can I do? How else can I interchange my variables? So I left three constants. So now I will keep one in its place and I interchange the other two variables, x3 square, x2 power 1. Okay, or I leave 2 in its place, x2 square, and I interchange 1 and 3. Okay, so 3, 2, 1. Okay, so I've done 3 of the permutations, but there are some more. There are these cyclic permutations, for example. Right? So what are my other permutations? I have cyclically shift the 3 variables. So 1 goes to 2, 2 becomes 3, 3 becomes 1. Okay, and the powers are still 3 to 1. Then there's the other reverse cyclic shift, which is 1 becomes 3, 2 becomes 1, 3 becomes 2. Okay, so 2, 3, 1 is one of them, and then 3, 2, 1 is another one. Okay, so 3, 2, 1, 3, 1, 2 is another one. So this will now become again cubed square 1. Okay, so that's so what have I done? I've sort of written out 6 terms, and now you can check that this resulting polynomial, this is a sum of 6 monomials, is actually a symmetric polynomial. Okay, why? Because any permutation of the variables I take, I'll get back the same polynomial. I'll get the same 6 terms, maybe in some other order if I permute the variables. But it's not just that. I can of course do more complicated things like I did earlier. I can say, okay, I take 4 times all of this plus, let's say, some other constant 3 times, maybe x1 plus x2 plus x3. Okay, this is also symmetric. Okay, so all I've done is just added to it an additional term and ensured that that additional term is also symmetric. Okay, so here are some complicated examples maybe, and as you can imagine, you can manufacture still more complicated examples as you increase the number of variables. Okay, good. So let's try and record the basic observation that we have made so far while we try to construct these examples. So something that we actually have observed already. So here's the proposition. It says that okay, let's start with the polynomial. Let f of x. So x here again is a multi-index, many variables x1, x2, xn. So let f of x be a polynomial. So let me call it summation c alpha x to the alpha. So recall, any polynomial can be written like this, okay, with finitely many terms and c alphas being non-negative integers. So as described before. So let this be a polynomial in n variables. Then the symmetry of f, then f is symmetric, f is a symmetric polynomial. Is the same as saying that it says something about the coefficient c alpha. It says that the coefficient c alpha, that is the coefficient of the term x power alpha, is the same as the coefficient of the term x power beta, where beta is some permutation of alpha. Okay, so that's exactly what we have observed when we constructed these. So c alpha is the same as c, well, how shall we write this? So let's do the following. Let me write alpha out in full. So I'll call this c of the multi-index alpha 1, alpha 2, alpha n. That's the coefficient of the monomial x1 power alpha 1, x2 power alpha 2, and so on till xn power alpha n. This is the same as the coefficient of the monomial, where in place of alpha 1 I have some other alpha I. I have some permutation of these n guys. So let me call that permutation something. So instead of alpha 1 I have alpha tau 1. Instead of alpha 2 I take some other guy, alpha tau 2, and so on. Alpha tau n, where tau is some permutation of the numbers 1 through n. Okay, this should be true for all permutations, for all tau in Sn, and for all alpha as well, and all the multi-indices which are here. Okay, so observe, of course, most of the multi-indices, most of the coefficients are going to be 0. Right? Remember, only finitely many coefficients are non-zero. So this is really a statement about those finitely many non-zero coefficients. That if some coefficient of some monomial is a certain number, then the coefficient of the permuted monomial should also be the same number. Okay, and observe, we already saw this in this earlier example. So what did we have? If you looked at all these monomials here, so this, and so on, these 6 monomials which correspond to permuting, think of it as permuting the alphas. Okay, so why is it a permutation of the alphas? So if you look at this, see this guy here, x2 cubed, x1 square, x3 is actually, so you can rewrite this term as follows. So let me just rewrite this particular term here. This term is the same as, I'll read it in the correct order, x1 followed by x2 followed by x3. Then I can think of it as 2, 3, 1. Okay, in other words, I can either think of it as, so this particular term is equal to this. So I can either permute the variables, or equivalently I think of the variables as being fixed in their places, but the exponents are being permuted. So observe, instead of 3, 2, 1 being the exponents, this guy has 2, 3, 1 as the exponents. Okay, but now the x1, x2, x3 are written in the correct order. So that's really what's going on here, that all these 6 monomials can be thought of as follows. You fix x1, x2, x3 and you permute the alphas. Okay, and all permutations of the alphas, those different monomials that you get, all of them have the same coefficient 4. Okay, similarly, likewise, this monomial here, x1, x2 and x3, well, what do they correspond to? You should think of it as, this is x1 power 1, x2 power 0, x3 power 0. So it is the multi-index alpha is 1 0 0 in this case. Okay, and for the second term alpha for x2, what is it? It's 0 1 0. It's just x1 power 0, x2 power 1, x3 power 0. And this third guy x3 is just x1 power 0, x3 power. Okay, so 1 0 0, 0 1 0 and 0 0 1. Those are those three terms, and all of them have the same coefficient, namely a 3. Okay, so that's really what this proposition is saying, that if you write f, so here's the proposition, if you write f of x as a linear combination of monomials, then f is symmetric is the same as saying that the coefficients C alpha will turn out to be the same as the coefficient of the monomial, which is a permutation of alpha. Okay, good. So that's the first proposition. Proof is more or less obvious from what we have said before, but let's do it nevertheless. At least I'll indicate how to formally write this out. So let's prove the forward direction, which is if f is symmetric, then this particular property holds the coefficient equalities. Okay, so observe f is symmetric says the following. So f is given to be symmetric. So f is symmetric means what? So the defining property of symmetry says I can permute my variables and the polynomial won't change. Okay, so let me take that same permutation. I'll pick a permutation tau. So I look at x tau 1, x tau 2, x tau n. This is true for all tau permutations of 1 to n. Okay, in particular, now what does that mean? I will expand the polynomial out. C alpha x to the alpha. That's the left hand side. Okay, f of x1, x2, xn. Whereas what's the right hand side? That's I have to permute my variables. So what does that mean? I keep z plus n, c alpha. And now remember, what is x to the alpha? So let's write that out. What is x to the alpha? This guy is just x1 to the alpha 1, x2 to the alpha 2, and so on. Now I should permute my variables, right? So what do? Instead of x1, I write x tau 1. Instead of x2, I write x tau 2, x tau n. But I keep my powers fixed. It's alpha 1, alpha 2, alpha n. That's what it means to expand and permute the variables. Okay, good. So that's an equality. But now we know the following, that the coefficients, so let's compare the same coefficient on both sides. So I'm going to compare the coefficient of x power alpha on both sides of this equation. So let's do that. So compare coefficients of x to the alpha on both sides. Yeah, maybe we should, let's choose a different, instead of alpha, let's choose a beta here, and I ask, okay, what's the coefficient of x to the beta on both sides of this equation? On the left hand side, it's easy. The coefficient of the monomial x to the beta is just c beta on the left hand side. Okay, now what is it on the right hand side? That's really the question. Okay, now on the right hand side, I need to pick out the monomial x1 to the beta 1, x2 to the beta 2, and so on, right? Now, when will I get that monomial? For which alpha in this summation will this monomial become the monomial x to the beta? Okay, so let's ask ourselves that question. So when will this become x to the beta? Let's do it on the side. So what I want is, well, I have this monomial here. So x to the tau 1. So I want this x tau 1 to the alpha 1, x tau 2 to the alpha 2, and so on. Tau n to the alpha, and I want this monomial to be the monomial x to the beta, which means it's x1 to the beta 1, x2 to the beta 2, etc. Okay, so this is sort of the observation we made. Either you you keep the powers in place and you permute the variables, or that same term you can think of as being obtained by keeping the variables fixed and permuting the powers. So that's what's going to happen now. So let's compare both these sides. Now I want to compare these two. I know that they are the same. So what does it mean? So let's see. Among these guys here, these subscripts, 1 will occur somewhere, right? So there will be some term for which this tau of that is 1. Okay. So let's call it something. Let k. Okay. Let k be such that tau k is 1. Okay. Then what does it mean? It means that what is the power I will get here? So on the left hand side, it will look like this. I have a bunch of terms and then I have xk power, x tau k power alpha k. Okay, and tau k is just the number 1 here, right? So this is just going to look like dot dot dot. So, these are the other earlier terms, and then this is x1. And then I have the power alpha k. Okay, so I know that these two have to be equal to each other, right? This term and this term are equal. What does that mean? It means that alpha k has to be the number beta 1. So that just tells me beta 1 had better equal the number alpha k. But what is alpha k? What was k really? K is a number such that tau k is 1. Okay. So this is just alpha of tau inverse of 1. Okay. K is just tau inverse of 1. Now similarly, you just continue with the same argument. You will conclude that beta 2 has to coincide with alpha of tau inverse 2. And so on. All the way till beta n. Okay. Or equivalently, one can invert this relation. Let's rewrite it as follows: equivalently. Let me write alpha. I can write it as this: alpha I is nothing but beta tau of I. For all I equals 1 to I. Yeah, it's the same thing. I've just rewritten it now in terms of tau rather than tau inverse. Okay, good. So what does that mean? Let's go back up. So we figured out, if I want to get this term to be the term x to the beta on the left side, then the alphas have to just be tau of the betas. Okay, so the coefficient that I'm going to get is just c sub tau of the betas. So therefore we conclude that the coefficient of the term x to the beta on the right hand side of this equation is nothing but c sub the alphas, where alphas are these guys, beta tau i's, beta tau 1, beta tau 2, and so on. Okay, and let's go back up. We already knew what the coefficient was on the left hand side, that was c beta. Okay, so I should have said the coefficient on the left hand side is this. Okay, so now the equality coefficients on left and right side are equal, therefore we conclude that the coefficient c beta must be the same as the coefficient c beta tau 1 beta tau. And this holds, observe, for all beta and all tau, right? So this is true for all beta. I can pick any multi-index I want, and I can pick any permutation I want. The same argument works. Okay, so that finishes the proof of the forward direction. So I'll just leave the converse as an exercise. It's more or less the same sort of idea. So reverse, try and work this out. Okay, so observe that we had already seen this in the previous example. So as I said before. Let's just quickly see how this played out there. So these the 6 terms on top, these 6 guys, 1 2 3 4 5 and 6, these 6 terms are all obtained there of the form x power alpha, some alpha and the various permutations of alpha. Okay, so 3 2 1, the powers get permuted. Now those 6 terms will all have the same coefficient C alpha. Similarly, these 3 terms x1, x2, x3, they are all just permutations of each other, the indices 1 0 0, 0 1 0 and 0 0 1, the multi indices, and those 3 will have the same coefficient 3. Okay.